Hello students, this is Bincy Joseph from the Department of IAC, AJIT, Mangaluru. In this video lecturing, we will be discussing about IPv4 addressing and subnetting. Under this, we will discuss classful addressing and classless addressing. Okay, first IPv4 addresses. IPv4 is nothing but Internet Protocol version 4. It is a 32-bit address that uniquely and universally defines the connection of a device, that is either a computer or a router. We call it as a host. You are connecting the host to the internet, and the length is 32-bit. Okay, all devices connected to the internet using IPv4 should have unique address without ambiguity or say conflict. It is 32-bit long, means see the available address space. If it is 32-bit long, means how many address space we will have? It is nothing but you will have 2 raised to 32 address spaces, available address spaces. How much is this? Just calculate. Okay, 2 raised to these many address spaces you can have. Okay, this many address spaces you can have. Okay, here see to this one of the address representation, 3 different notation in IPv4 addressing, that is a binary notation, decimal notation, and hexadecimal notation. We'll see to this binary and dotted decimal first. Okay, in the binary notation you have 32 bits, right? That means you have 4 bytes. 1 byte, you know that 1 byte is equal to how many bits? 8 bits, right? So you have 4 8 bits here, that is 4 bytes. This forms an address. The same dotted decimal notation is given here. So this is 128. Why this is 128? How? That is, say it is the first bit is 0, right? Here this is 2 raised to 0, which is this position, 2 raised to 0, 2 raised to 1, 2 raised to 2, 2 raised to 3, 2 raised to 4, 2 raised to 5, 2 raised to 6, and 2 raised to 7. What is 2 raised to 7 now? It is 128. Okay, that is your first byte. So in the decimal notation you represent it as 128 dot this in the decimal notation we use this dot to separate the bytes. Okay, next 11 half. This is 2 raised to 0 and 2 raised to 1 here, and 2 raised to 2 is 0, 2 raised to 3, isn't it? What is 2 raised to 3? 2 into 2 into 2. 8. 8 plus, this is 2. 8 plus 2 is 10. 10 plus 1. 2 raised to 0 is 1, right? That is 11. Okay. Next, the third position is 3. That is 2 raised to 0 plus 2 raised to 1. That is 3. Dot 31. That is 16 plus 8 plus 4 plus 2 plus 1. That is 31. Hope you understood, right? If you get a binary like this, now you can convert it to decimal, dotted decimal, isn't it? And in reverse also, if you get this decimal number, you have to convert it into binary in the form like this. Okay, 32 bits you have to consider, and for 8 bits each, that is in total 4 bytes. This is how the address is denoted. Okay, next we will see the hierarchy in addressing, that is, a 32-bit IPv4 address is hierarchical but divided only into two parts. That is, see, out of this 32 bits, you will have one prefix. This is the prefix, and suffix. The rest is the suffix. Okay. If I say n bits is the prefix, then 32 minus n bits is the suffix. So this n bits will represent the network ID, overall ID here. Okay, it will define the network ID, or you can say it as net ID. Okay, and this 32 minus n bits here will represent the that is a host ID, that is inside the network. Whatever addresses is there, that is represented by the suffix, defines connection to the node. Node means any computer or routers or whatever it is. Okay. Now, classful addressing. First type, that is classful addressing. When the internet started, an IPv4 address was defined with a fixed length prefix. That is, the length of the prefix was fixed initially when this internet started. Okay, and we call it as classful addressing. To accommodate both small and large networks, three fixed length prefixes were defined instead of one. Those were n is equal to 8, n is equal to 16, n is equal to 24. So in IPv4 classful addressing, the address space is divided into five different classes, that is A, B, class C, class D, and class E. Now we will see to each of these classes. Here, see, in class A, this shows the classes and the first byte range and the prefixes. Okay. Now, here in class A, the first 8 bits, this 8 bits here, see, the prefix 8 bits, this will be containing the, which ID this is? It will represent the network ID, and the rest, how many bits are there? 24 bits. This 24 bits will represent the host ID there. Okay. And in class B, here in class B, the first, how many bits? 8 plus 8, that is 16 bits will represent the network ID, and the rest of the bits, that is again 16, will represent the host ID. In class C, 24 bits, initial 24 bits will represent the network ID, and the last 8 bits will represent the host ID. This way you have class A, class B, and class C. Okay, and here in class A, if you could see, the first bit will be 0. That is, this bit is permanent. This bit is used to represent that it belongs to class A. And the rest, that is, if this is 1 bit, right? 0 is 1 bit. Rest you have 7 bits here. This has the flexibility, means you can change. For next 7 bits, it can have all 7 bits 0. Either you can have all 7 bits 0 here, or you can go up to all 7 bits as ones. If you make all 7 bits as ones, then you will get how much? 128 to raise to 7. So the range here is given as 0 to 127. N is equal to 8. Okay, that is this prefix length. class. Similar way for class B, that is the initial 2 bits. Out of this 16 bits, 2 bits are meant for which one? The to represent that it is class B, that is 1 0. Okay, and the rest, how many bits are there? 14 bits. You can have the flexibility here. Okay, for this 14 bits. So what is the range? That is 128 to 191. You can represent from 128 to 191. Okay. Next, you have class C, that is that is 110. That is, this will represent the class C, and the rest we can have the flexibility. Out of how many bits? 24 bits. If 3 goes, the rest, that is 22 bits, you can have flexibility. So the range is how much? 192 to 223. Okay, and class D represented by 110, 1110, and the rest multicast address. Class E with 1111 and reserved for the future, that is 240 to 255 range. Okay, in detail we will see one more table here, which represents the number of blocks and block size here. See here, in class A, the number of blocks is 128 from the previous table. See here, 0 to 127 means you can have 128 blocks there. Okay. Now, if you have 128 blocks, for each block you can have this much block size here. That is 16 mega block size. How is it 16 mega block size? It is nothing but, see here, you can have 8, n is equal to 8 bits, and you can have 0 to 127, isn't it? That is 128 blocks here. So this block size is 16,000, that is 2 raised to 128, that is 16 mega, this much. See, from the previous table, for class A, the prefix is 8 bits and the suffix is 24 bits, right? Okay. So here, if you see, for class A, the prefix here is 28 bits, right? And the suffix part, suffix is how much? 24 bits. So how many addresses you can have here? It is 2 raised to 8. Number of blocks is 2 raised to 8. That is 220. 2 raised to 7. That is 128 number of blocks. Okay. And the block size here is 2 raised to 24. How much it will be? 2 raised to 24 is the block size here. How? 24. That is equal to, you can say that is 2 raised to 4 into 2 raised to, for your easiness I am telling, okay, 2 raised to 10 into 2 raised to 10. Okay, this is 2 raised to 24, right? So This 2 raised to 10, you can say it is 1K. Okay, and this is also 1K. And 2 raised to 4 is 16, right? Okay, now, so this size, block size is 16. 2 times of K is mega. 16 mega is the block size here. 16 mega. Understood? Here, 16 mega means 1K is nothing but how much? It is not 1000 but 1024. So you multiply and see. 1024 it is. 16 into 1024 into 1024. You will get the 16 mega here. This is how block size is calculated. Again, for class B, if you say, for class B, the block size, how to calculate the block size for class B? It is previous table. You see what is the suffix here? It is 8 plus 8, that is 16 bits. So suffix is 16 bits. So how much it is? 2 raised to, how many, what is the block size? 2 raised to 16. That is equal to 2 raised to 6 into 2 raised to 10. How much? It will give, this is 1000, isn't it? And this 2 raised to 6 is how much? 64. So 64K. Roughly you can say 64K. Now you might ask me why this is 65,000. 1536. I told you 1K means how much it is? 1024, right? So if you multiply this 10, that is 2 raised to 10 is 1024. Okay, you have to consider 1K as 1024. So 1024 into this 64, you will get 65,536. Okay, similar way for class C also you have to calculate it like that. That is what is the number of bits in the suffix for class C? For suffix, how much is, what is the number of bits? It is class C. See here. What is the number of suffix? It is 8. So it is 256. 2 raised to 8. That is 256. See, now what you can infer from this is, here the blocks means this blocks, the number of blocks. These blocks means how many number of net IDs you can have. Understood? These are the these many number of net IDs, that is network IDs you can have, and for each network ID you can have this many number of host IDs, or say you can install these many number of nodes to this net IDs. Understood, right? This represents the total number of net IDs you can have, and this is the block size for each net ID. How many number of nodes you can install for each net ID. Okay, next we will see the mask. Okay, how to mask this? Okay, now for class A, the prefix is how much? The prefix is represented by 8 bits, and the rest is meant for the suffix, right? So this prefix, that is the reserve, that is for the net ID, all these bits you represent it as ones, and for the suffix all the bits you have to represent it as zeros. This is how it is masked for class A, how the masking is done. Okay, now in dotted decimal you can say this is how much 2 raised to 0, 2 raised to 1, up to 2 raised to 7, right? That is 255. This in dotted decimal you can say 255 dot 0 dot 0 dot 0. This is the mass for class A. Here you have slash 8. That means it means that these 8 bits are will represent the network ID. This one. This is the slash notation. Okay, and here in class B, the next, that is first 2 bytes will represent the network ID, and the rest 2 bytes, these 2 bytes will represent the host ID there. Okay, that is slash 16. These 16 bits represent network ID, and the rest for the host ID here. Again, for class C, what is the slash notation? Slash 24. That means 24 bits will represent the network ID, and the rest 8 bit will represent the that is host ID. This slash notation is also used to separate the network ID from the host ID here. Okay, and also you can have a slash notation, this one, which represents how many bits are representing net ID. So it differentiates between net ID and host ID. This slash notation is also called CIDR, that is classless interdomain routing. That is in classful addressing, whatever we discussed now, a good number of available addresses is wasted. So it has been replaced by the classless addressing, which we will discuss next, using this slash notation here, which is also called classless. CIDR means classless interdomain routing. Okay, before moving into the classless, we'll see this subnetting, supernetting, and address depletion in this classful. Subnetting is if an organization was granted a large block in class A or B, it could divide the addresses into several group subnets and assign each group to smaller networks called the subnets, or they can share the addresses with neighbors as well. Okay, in supernetting, an organization combines several C blocks, third class, okay, to create a larger range of addresses. In other words, you can say several networks combine to create a supernet or a super network. Now, that is the disadvantages in this classful addressing scheme combined with the fast growth of internet led to the near depletion of the available addresses. That is number of available addresses were very less. So we started with the concept of classless addressing. Now we'll see how the address blocks are represented. The addresses in the block must be continuous in classless addressing. Okay, this classless addressing, it was designed to overcome the address depletion and give more organizations access to internet. And there are no classes like classful addressing, but the addresses are still granted in the form of blocks. Okay, now if I say blocks, address blocks, and these address blocks must be continuous one after the other, and the number of addresses in the block must be a power of 2. That is here, for example, power 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3 and so on, like that. And mask, how to mask the classless addressing. Here you can mask it as how much a block of addresses can be defined as x dot, that is in the decimal, dotted decimal, x dot y dot z dot t slash n. Here this represents the slash notation or CIDR, classless interdomain routing. That is, this will give you the number the number of bits which represents the network ID. For this, if I say, let me give one example of this. For example, consider one address, that is 2.16.37.39 slash 28. Okay, yeah, when you get a representation like this, the address like this in classless addressing, here slash 28 means when you convert this decimal part into 4 this one, that is binary notation, that is you will have 4 bytes, isn't it, which represents this. 1 byte will represent this, next byte will represent this, next byte will represent this, and next byte will represent this. That means total 32 bits will be there. 32 bits will be there. So now out of this 32 bits, the initial 28 bits, in the slash notation it is given 28, right? So initial 28 bits will represent the prefix. That means it will represent the network ID. And the rest, that is how many is there, 32 minus 28, that is 4 bits will represent the suffix, that is the host ID here. Next is network address, how to identify the first and the last network address. See, to identify the first address in a block, if you get this one, that is a address like this along with the slash notation, to identify the first address, what you have to do is, from our previous example, say this 205.16.337.32, here you have the binary notation of that same. Okay, 33. Here what happens is, if you want the first address, this one, first address in this particular block, then in the suffix part, how much ever bits is there, that bits you have to represent it using zeros. That will give you the first address in the block. And if you want the last address in the block, then see, if I say till here, it represents the, okay, till here if it represents the prefix, then this is suffix part, that is 4 zeros are there now in the suffix part. This suffix part, if you represent it as 1 1 1 1, then this will give you the last address in the block. See here, the last address, how it is represented. Understood, right? So in the to get the in a block, how to get the first and the last address? The first address you can get it by putting zeros to the suffix, that is 32 minus n. N is nothing but, if n is the prefix, then 32 minus n those many bits in the rightmost end you have to put zeros to get the first address, and the last address by putting replacing the suffix bits by ones. Okay. Okay, so from this, if I say the same concept what I told you, if you want, this is the prefix and this is the suffix, that is 28 bits if it is the prefix and 4 bits if you have the suffix. Here in the last 4 bits, if you represent it as zeros, you replace all the bits whatever you have with the zeros, or you can use the AND operation here. You will get the first address in the block. Okay, else if you replace it with the ones in the suffix, you will get the last address. Understood? Now here this shows the hierarchy here. 2-level hierarchy in classless addressing. That is, you have for example, if you have 32 bits representing the address, out of that 28 bits represents the prefix and 4 bits represents the suffix, then this 28 bits is the network prefix and this 4 bits is the host address. This is 2-level hierarchy. 3 levels of hierarchy, that is a subnetting. More levels. Okay, that is, you will have a host subnet ID as well. See, for an example, an organization that is granted a large block of addresses may want to create clusters of networks, that is subnets. That is, an organization is assigned a large block, so that block you have to divide it into subnets and divide the addresses between the different subnetted. We'll see how to divide, how to find the mask for each subnet. The rest of the world sees the organization as one entity. However, internally there are subnets, that is a division of networks. And all messages are sent to the router address that connects the organization to the rest of the organization. Through the router, these subnets together forms a network, and it is connected to the outside network through the router. Okay. However, needs to create small sub-blocks of addresses, each assigned to specific subnets. The organization has its own mask. Each subnet must also have its own. That is, each subnet will have its own mask. This particular network will have one mask, and each of these subnets, yellow, pink, blue, all these subnets will have its own mask. Okay. Now, to the rest of the internet, you're connecting to the router. Okay, the address format is as we discussed. It is x dot y dot z dot t /n, that is slash notation, or you can say CIDR, classless interdomain routing. Here, now from the router you have the address, that is 17 point, and an example is given here, 17.12.14.0 and /26. That means in this 32 bits, 26 bits will represent the network ID. Okay, 26 bits will represent the network, and the rest, how much is it? 32 minus 26, that is 6 bits to represent this particular network, whole network here. This one, 6 bits you can use to represent this particular network. 6 bits to represent this particular network means how many addresses you can have here in total? That is 2 raised to 6. How much is 2 raised to 6? It is 64. So you can have a total of 2 raised to 6. That is 64 blocks. Okay. Now, how to divide this 64 addresses among 3 subnets? We have to divide 64 into 3 subnets, right? That is, you can divide it as one block with the 32 addresses, one with the 16, and one more with the 16. Isn't it? 32 plus 16 plus 16, you will get 64. Now, for each of these, this one, that is the subnet, you have to find the mask. How to find the mask for each of these subnet? See, for this first subnet, we are going to assign 32 addresses. Okay, 32. How do you represent 32? It is 2 raised to how much? 2 raised to 5, right? 2 raised to 5. That means you need 5 bits to represent these 32 addresses. Okay, 5 bits to represent this 32 addresses means 5 is your suffix. Okay, now when 5 is your suffix, what would be your mask? It is 32. Your mask will be 32 minus 5, isn't it? 32. Out of 32 bits, you need 5 bits to represent the address in this first subnet. So 32 minus 5, that is equal to 27. So for the first subnet, the mask is 27. See here in the diagram. Slash 27. So each of these hosts is represented by the mask 27. From where to where? This is 17.12.4. Here 1 to 31 here. That is 32 addresses. You can connect 32 host computers to this particular subnet. Okay. Similar way, for the second subnet here, how many addresses you will get? How many addresses you are going to allocate for this second subnet? 16. If you want to represent 16 addresses, what is the mask? That is 16 is represented by 2 raised to 4, isn't it? 4. That means 4 bits are needed to represent this 16 addresses. So what is the mask? Mask is 32. Out of 32, total address is represented by 32 bits. So 32 minus this 4, that will give how much? 28. So the mask for this particular subnet is how much? It is 28. See here 17.12.14.46 slash 28. This is how you get the mask here. Okay. And what are the addresses starting from till 32? You will be representing in this subnet. After 32, that is 33 to 33 plus 16, that is 48 till 47. You can represent here. These many addresses you can allocate to this host. Similar way here also you have 16 addresses. How to represent? 16 is equal to 2 raised to 4, and the mask will be 28 again. Okay, 28 again, and this 28 from where to where? The address will start from 49 to 63. So in total, this particular network will have 64 addresses. 1 to 32 here, 33 to 47 here, 48, then 49 to 63, here in this third subnet. Understood, right? If an address, see, if there is, you have an packet for the address 17.12.114.50, then where it will go? It will go to, this router will route it to which subnet? That is to this third subnet. Why? Because the range in third subnet is 49 to 63. So this packet will be routed to the third subnet here. Okay, from the outside world, it will route to this subnet. By looking till 14, it will route to this one, and it will send to the subnets. This router will send it to the respective subnets here. Okay. Next, we will consider one more example to understand clearly, along with the formula to find the mask as well. What formula? This is analyzing, by analyzing, isn't it? Other than that, you can use the formulas as well. We'll see to the next example. Okay. Example, an organization is granted a block of addresses with the beginning address of 14.24.24.0/24. What is it? This is the network. 24 bits will represent the network ID, and the rest, how many bits will represent the addresses, subblocks? How many addresses are available? That is 6 plus 2, 8. So 2 raised to 8, isn't it? You will have 2 raised to 8. Okay. The organization needs to have 3 subblocks, that is N1, N2, N3 of addresses to use in its 3 subnets. Out of this 256, you have to divide this 256 into 3 subblocks. And here the subblock, how many addresses should be there in the subblock? They have given in the question itself. That is one subblock of 10 addresses. Second subblock, it is 60 addresses, and one more is 120 addresses. These many addresses should be present in the subblocks. Design the subblocks. We have to design the subblock now. Initially, I told you the address blocks should be a power of 2, isn't it? So, first we will consider this third subblock, okay, starting from this one. Before that, we'll see how many addresses you need, as I told you. That is here. What is the CIDR? 24. That means for the to represent the network ID, you need 24 bits, and the rest bits, that is 32 minus 24. That is how much? 32 minus 24 is 8. 8 bits you need to represent the number of block size it is. That is 256 addresses are available. Okay. In this block, the first address is 0.0. The last address is, how to find the last address? The last 8 bits, make it as 1. So how much you will get? It is 255. The last address is 255. Okay. Next, to satisfy the third requirement, we assign addresses to subblocks. This third one, starting with the largest and ending with the small one. We'll start with the first block, that is 120. We'll consider the number of addresses in the largest sub block, which requires 120 addresses. You have to, for the first subnet, you have to allocate 120 addresses, but this 120 is not a power of 2. So you have to make it to the power of 2. That is which is near to 120. It is 128. That is 2 raised to 7. 128 means how much? 2 raised to 7. This one, okay, 128, 2 raised to 7 addresses. The subnet mask for this subnet can be found as, how to find the subnet mask now? See, this 7 bits you need to represent how much? 128 addresses, isn't it, in that particular block. So what is the mask to be used then? 32 minus 7. Okay, that is how much? 25. This 25. This is how you get this 25. Or else you can use 32 minus n1. You can find using 32 minus log 128 to the base 2. You'll get 25. This is the mask. The first address in this block is 14.24.74.0, and the last address is, that is how many addresses it will have? 128. So the last address is 0.127. So the first block we got it, that is, it will assign the address from 14.24.74.0 to 14.24.74.127. Understood, right? 0 to 127 it will assign, that is 128 addresses, and the mask is 25. Now we will consider the second one. Second largest block was in the question. How much? What was the second largest block? It was 60. Now we have to assign 60 addresses into the second sub block, but 60 is not a power of 2, so make it to the power of 2. That is, you can have 64. How to represent 64? 2 raised to is represented by 2 raised to 6, isn't it? That means you need 6 bits in the suffix part, isn't it? That is, to represent 64 address you need 6 bits. So 32 minus 6, how much is it? It is 26. So the subnet mask is 26. Else you can use this formula. Okay, it is up to you. 26. The first, so the first address in the block will be, see, till 127 the subnet 1 will occupy the address. From 128 you can start the second subnet. 128 plus how much? How many addresses here we are going to allocate? That is 64, isn't it? 128 plus 64, that is 192. So you can have 128 to 14.24.74.191. Till this address you can allocate 191, and the slash notation or CIDR is 26. Next, the third number of address in the question it was given 10, but 10 you cannot assign. So what happens? You have to represent it in the form of the power of 2. That is, you can take 16. 16 is nothing but 2 raised to 4, isn't it? So 4 bits to represent 16 addresses. The rest is 32 minus 4, that is 28 bits for prefix. The first address here will be starting from the second block. Last address in the second subnet is 191. So here we will start with 192 till how much? Plus 16. These 16 addresses you have to accommodate, right? Plus 16, that is equal to till 1207. But here you have used till 207, means you have used in total 208, 0 to 208, isn't it? But how many addresses was there actually? It was 256. Till 208 you have used. So what is the left out? 256 minus 208, that is almost 48 addresses is left out, which we can use it for the future. Understood, right? 48 is reserved, we can reserve it for the future. Now we have divided the block. The same thing, whatever we discussed, we'll see the diagrammatic representation, so that you will be more clear about this. Let us see to this diagram. Here, see, initially you had 256 addresses, isn't it? That is 2 raised to 8. Okay, starting from 74.0 to dot 255. Okay, out of this, for the first sub block, you allocated 128 addresses, that is starting from 0 to 127 here. Next, and the mask was 25, subnet mask 25. And next, for the second block, you allocated 64 addresses with subnet mask 26, starting from the address 128 to 191 here, last address. Next one with the 16 addresses, that is 192 to 207. Okay, and yeah, you can use it for unused space, that is next 48 addresses. Thank you, students.